Hello and welcome to Algebra 1 with Miss Betsy. Glad you're back with us today, where we are going to be learning how to multiply together radical expressions. And we're going to see that it's not quite as different as you might think it would be. Before we get started though, I want to know if any of you have heard about this reporter who was interviewing a lady who had attained the ripe old age of 103. And one of the questions that he asked her was, can you tell me, ma'am, what it is that is the very best thing about being 103 years old? She looked right back at him, didn't bat an eye, and said, there is just no peer pressure. So, you only think you have peer pressure as teenagers, and so this 100-year-old lady is glad that there's no more peer pressure by the time she gets to be 103. So, I've already written a definition up here on the board. Want to remind you that we are using as our text Algebra 1 for Christian Schools. It's published by Bob Jones University Press. I'm using the second edition. I'm in Chapter 10, Section 8, Multiplying Radical Expressions, and I'm on page 428. You don't have to use this text. Multiplying radical expressions is the same across the board regardless of what text you use. First off, what is a radical expression? Well, a radical expression is an algebraic expression that contains at least one radical. An example might be square root of 3 plus 2. Another example might be square root of 5 minus the square root of 7. Another example might be the cube root of 62 plus 6. Another example might be the cube root of 21 xy cubed z squared. You know, all a radical expression is an algebraic expression that contains a radical symbol somewhere in there. We have two parts to this. We have just a single cube root over here. And we see that these are not, what's my word? Let me look here. These are not polynomials, because you might think, oh, well, that sort of looks like a polynomial. The square root of 3 plus 2 sort of looks like a binomial, x plus 2. It's not the same as a binomial, but we're going to find that we multiply algebraic radical expressions similarly to how we multiply binomials, and that's where it sort of becomes a little bit of fun. You're saying, you know what, Miss Betsy, it's way too early in the morning for you to be talking about math being fun. Well, you got a choice of thinking, okay, I know I've got to do my math here. Mom and Dad are making me do it, or I know I've got to get a good grade so I can do well on the SAT, or you've got to do the math because this job that you have lined up down the road, you know you've got to have a good math foundation. So just decide you're going to have fun. It makes your day not quite so bad. Let's go ahead and look at example number 1 on page 429. Square root of 5 times quantity square root of 3 minus 2. Square root of 5 times the quantity square root of 3 minus 2. This is a very simple distributive property. You have one factor outside the square root of 5, which you have to multiply with each term inside the parentheses. First you have the square root of 5 times the square root of 3. Next, square root of 5 times negative 2 becomes minus the square root of 5 times 2. Does everyone see exactly what I did here? All I'm doing is distributing a factor of the square root of 5. Square root of 5 times the square root of 3, we use our product rule to say, well, first off, we're looking here. Can we take the square root of 5? No, it's a prime number. You can't take the square root of 3 either because it's a prime number. We use our product rule this becomes the square root of 15 minus, what is the square root of 5 times 2? Is it the square root of 10? No, it's just 2 times the square root of 5. When you have a radical like this, put your whole number portion in front of the radical. So we have 2 times the square root of 5. Now what we need to do is combine like terms. How do you determine whether or not you have like terms when you have radicals? Well, the number underneath the radicand has to be the same, and the index has to be the same. The index here we understand to be 2, so of course they're both square roots, but we have a 15 and we have a 5. They're not like terms. It's like saying we have x minus 2y. So the solution to our problem where it's said to multiply the square root of 5 times the quantity, square root of 3 minus 2, is, and you're going to laugh when I say simply, it is simply the square root of 15 minus 2 times the square root of 5. There's nothing else that you can do there, nothing that you can combine, no perfect squares to factor out here. This is our solution. So let's go ahead and look at example 2 on page 429 and see what we have here. And our instructions say multiply the square root of 5 minus the square root of 7 times the quantity, the square root of 5, plus the square root of 7. Now remember I said that radical expressions are not polynomials, but they can be treated and multiplied as if they were polynomials. If you look at this, what does this remind you of? Or what should this be reminding you of? This should be reminding you, see if I can stay in the screen, of x plus y times x minus y. X minus y, x plus y. What we have here is the factored form of the difference of two squares. How did you learn the shortcut to multiply this? Remember, you had learned FOIL when you multiply two binomials together. You have 4 partial products. Multiply the first terms together, plus the outer terms multiplied together, plus the product of the inner terms, plus the product of the last terms multiplied together, and that gives you the complete total product of two binomials. But we also noticed that when we had something that looked like this, this was the factored form of the difference of two squares. What you did for this was you took the first term and you squared it, and then you subtracted the square of the second term. So that's what we're going to be able to do here. We're going to have, in blue, square root of 5 squared minus the square root of 7 squared. What's the square root of 5? Well, the square root of 5 is, it's very interesting, I'd love to know where this came from. This is actually example 3 if you're trying to track with me in your book. My eyes went down. Square root of 5 squared is 5, minus the square root of 7 squared is 7. You subtract those, and the solution, or the product of the multiplication of these two radical expressions here, is a -2. So we're going to be using all of the techniques and all of the patterns that we learned when we were multiplying polynomials together, except we're going to be applying them now with radical expressions. So let's go ahead and back up for a moment to the second example that I skipped. I'm going to go ahead and pick up the book here. we're going to multiply square root of 7 plus the square root of 2 times the quantity square root of 3 minus 6. These are not binomials, but they look like binomials. You know, polynomial expressions have to have the variables in there. There are no variables, but this is still going to function. Do we recognize any special products here? No, but we can use FOIL. We can use our acronym to multiply together 4 different sets of factors to give us the total product. The F, we're going to multiply our first terms together. What's our first terms? The product of that, we have the square root of 7 times the square root of 3. Does everyone see that? Square root of 7 times the square root of 3. Make sure you're showing me all your steps. Make sure you're doing all of the work. Do not try and do these things in your head. It will not help you at this point. Now we're going to do the product of the outer terms. We have square root of 7 times the negative 6. So it becomes minus 6 times the square root of 7. Switched it around to put the whole number portion in front of the radical. The I represents the product of our inner terms, plus the square root of 2 times the square root of 3. And this is starting to look pretty messy, isn't it? It is starting to look messy, but it is what it is. What's our final partial product here? Represented by the L's. That's where we multiply the last terms together. Square root of 2 times a negative 6. That becomes minus 6 times the square root of 2. Okay? Do we have any perfect squares here? No. They're prime numbers. Square root of 7 times the square root of 3, using the product rule, gives us the square root of 21. Minus 6 times the square root of 7. We're going to use the product rule again. The square root of 2 times the square root of 3 gives us the square root of 6, because there are no perfect squares. All of these numbers underneath the radical symbols here are prime numbers. And our final, minus 6 times the square root of 2. Have a big long string of mess here. Surely we can simplify this. We can combine like terms. What did we say like terms are when you have radicals? You have to have the very same number underneath, or the very same expression, underneath that radical symbol. None of them are the same. There are no like terms. This is like saying x, y, z, and a. This string right here is what happens when you take the product of the square root of 7 plus the square root of 2 times the quantity square root of 3 minus 6. You know, your eyes are getting big and you're sort of glazing over a little bit. Apply everything that you've already learned. You know how to FOIL. You know how to multiply radicals together. And you know how to recognize what like radicals are. None of these numbers are the same. There's not a thing you can do. Okay? Go ahead and look at example 4. Square root of 3 minus 2 squared. Again, not polynomials, but you treat them as though they are polynomials, where we have a perfect square trinomial. And I want you to go back, because some of you learned this, some of you didn't. So I'm going to see where we have perfect square trinomials. Let me look in my index. right here. I think it's back in chapter 8. Factoring perfect square trinomials. Probably section 8.7. Let me look and see as we pause just long enough. Special products, squaring a binomial, difference of squares, dividing. Okay, of course I can't find it right away, but I do know that if you look on page 371, it's chapter 9, section 3, you're factoring perfect square trinomials. What a perfect square trinomial is where you have a binomial looking expression that you're using as a factor twice. This has a pattern. How do you work with perfect square trinomials? When you're multiplying this out, you have the first term squared, then you use the sign in this factor here in front of your center term minus twice the product of the first term and the last term plus the square of the second term. Okay? You don't even have to put that negative sign in there because when you square a negative number, your answer is always positive. Square root of 3 squared is 3 minus 2 times the square root of 6 plus 2. Do you see what I've done there? Square root of 3 times the square root of 3 is 3. There are no perfect squares underneath these radical symbols here. Our product rule tells us that the square root of 3 times the square root of 2 can be written as the square root of 6. Square root of 2 squared is going to give us 2. I totally lost the page that I'm on while I was looking for perfect square trinomials for you. Let me find my page. We're back on section 10.8. I made up a problem. This is a good one to use. 3 minus 2 times the square root of 6 plus 2. 3 plus 2 is 5. Minus 2 times the square root of 6. Is there anything else that you can do there? No, but you have to understand how to work with patterns that are similar to doing perfect square trinomials. Square root of 3 squared minus twice the product of the terms plus the square of the second term gives us 5 minus 2 times the square root of 6. Okay, let me go ahead and use the actual problem that they gave to us, which is a little bit easier. So you'll say, oh, yeah, this is simple. Square root of 3 minus 2 quantity squared. We'll just get rid of a few of the radical symbols. This is perfect square trinomial pattern that we're using to multiply this together. Square root of 3 squared minus twice the product of the terms. Square root of 3 times 2 plus the square of the last term. And it's actually minus 2. I should show that. Say negative 2 squared. Square root of 3 squared is 3 minus 2 times 2 is 4 times the square root of 3 plus 4. We're going to go ahead and combine like terms. 3 plus 4, 7 minus 4 times the square root of 3. Recognize patterns from when you were dealing with multiplying and factoring polynomials, and this will help you when you're dealing with the multiplication of radical expressions. Cannot say, man, Miss Betsy, I just haven't been able to learn my formulas for the perfect square trinomials. Isn't it true that this simply says use the square root of 3 as a factor twice? So couldn't I use FOIL to find this product? Yes, you can. Product of the first terms, we have the square root of 3 times the square root of 3. The outer terms, minus 2 times the square root of 3. The inner terms, minus 2 times the square root of 3. The product of the last terms, negative 2 times the negative 2 is a positive 4. What do we have now? The square root of 3 times the square root of 3, square root of 9, minus 2 times the square root of 3, minus 2 times the square root of 3, that gives us minus 4 times the square root of 3, plus 4, 3 minus 4 times the square root of 3 plus 4, because the square root of 9 is 3. Now we combine like terms, 7 minus 4 times the square root of 3. And you see that we arrived at exactly the same answer by using the process known as FOIL, where we do 4 partial products together, instead of recognizing that this can be treated like a perfect square trinomial. Either way works. They're trying to get you to recognize patterns to save yourself some time. So, let me go ahead and see if I want to do one more problem for you. Let me go and use one where we have 3 factors. And that will be my final example that will work on this problem. I'm on the top of page 430 now. I do want to say they're telling you what to do for multiplying radical expressions. It's exactly what we've been talking about so far. Follow the same rules that you apply for multiplying polynomials. After you multiply, you simplify the radicals and you combine like terms. Sometimes people like to see something written out. Our problem here says multiply square root of 3 minus 2 times the square root of 3 plus 2 times the square root of 6 minus 4. So how many factors do we have in this problem here? We have 3 factors. I'm going to multiply my first 2 factors together to begin the problem. And I am noticing that I am not going to FOIL this product. And why is that? Because this is the difference of 2 squares. The factored form of the difference of 2 squares. The terms inside these factors differ only by a sign. So the product of these 2, it's the square of the first term minus the square of the second term, still multiplying square root of 6 minus 4. What is the square root of 3 minus the square root of 2? Well, the square root of 3 is 3 minus the square root of 2 is 2 times the square root of 6 minus 4. Let me make sure that I'm going down the right path here. See the difference? This is what I was verifying. Remember how I talk about grouping is so important? Look at the difference. This would be 3 minus 2 times the quantity, square root of 6 minus 4. But I'm taking this product first, so I have to complete this multiplication. So what do I have here? I have 3 minus 2 is 1 times the quantity square root of 6 minus 4, which of course gives me the product square root of 6 minus 4. And these are the only examples that I'm going to do. Be careful. You can get tripped up on one tiny little thing by forgetting to enclose your work in parentheses so that you keep track of what products you have, of the order of operations that you need to be using to come up with the proper answer. Do not rush through these. Make sure that you take the time to show your work. Remember the things that you learned, the skills and the techniques, the shortcuts that you learned when you were multiplying polynomials. Remember to simplify your radical expressions before you combine like terms, and you will do just fine. Take your time, work through these, and I will see you next time around.